Hello, everyone. Today we're going to go ahead and do Vesper. I know you got a little bit of an introduction last week with that lab with Play-Doh. Or just a simulation if you had to only do the simulation. So hopefully you have some basis. Also there I posted that Vesper chart and I would absolutely make sure you have that ready for this section. And if you didn't see it there, it's also in week 3 where the video is, okay? So we've been drawing everything in 2 dimensions, and normally in the real world, things are 3-dimensional. So we have to keep that in mind. I am never going to ask you to draw them 3-dimensional, but you do need to be okay if you see them in a 3-dimensional space. Okay? This theory, Vesper theory, which we'll talk about what that means in a minute, it's going to show us the shape of the molecules, which is super important. Okay? And because we're in 3 dimensions, we're now going to have angles. So there's going to be different bond angles we need to focus on. Okay, so Lewis theory is going to go ahead and predict those electron regions, which are on the chart. So we'll talk about that. It's also going to be able to show us the extend. So we're going to extend our learning to predict the shapes of the molecules. Okay, so Vesper, which is what this entire, that's really the reason we draw, is because of Vesper, and that's the valence shell electron pair repulsion theory. So what the electrons are trying to do is to be the most stable and as far apart as possible. And that's what the Play-Doh lab was trying to get you to do. Okay, so, and generally they're in 3 dimensions. A couple of them are only in 2D. But when they're in that most stable configuration, their angles should be either all the same or only 2 different angle choices to be as far apart as possible. So, for electron groups, remember, each lone pair is 1 electron group, and each bond, not each single bond, all bonds count the same for electron groups, single, double, and triple. So here I've got 1 electron group, 2 electron group, 3 electron group total. So for this nitrogen, I have 3 electron groups. I also want y'all to make note, probably on that chart. If it were me, I would print that chart out that I posted so you can use it on your test. But the central atom is all we care about for Vesper. Okay, yes, you still have to draw your Lewis dots correctly, because if you don't, then it's going to mess with your double and triple bonds. And you may not have the right numbers of bonds. But we only pay attention to the central atom for those electron groups. All right, so there's 5 basic arrangements. There's 2, 3, 4, 5, and 6. And then there are variations of each of those. Okay, they are all on the chart. So the first one is having 2 electron groups. That's linear. It makes a line. That one's pretty easy. The angle of the line's 180, so just use that. The next one with 3 total electron groups is trigonal planar. All right, so this is still on a plane, which is why it's called planar. And there are 3 of them, which is why it's called trigonal. And the bond angle for them is 120. Next electron group is tetrahedral. Tetra is 4, remember that from naming. And hedral means faces. So this molecule has 4 faces, so it kind of makes a triangular pyramid, and then it's got that bottom face as well. Also, this one kind of looks like a tripod. Now, this is our first one that's in 3 dimensions, so this bond angle, you can't just take 360 and divide it, because now we're looking at 3-dimensional space. It's 109.5. So in which electron geometry do we consider only the electron groups on the central atom? Oh, in determining. Why do we only consider the electron groups on the central atom? Why don't we consider those on the terminal atoms? And that's because the geometry of the whole molecule is based on the center, not on the outside. So we only pay attention to the center because that's our basis for the whole thing. So here we have an example. First thing you should always do, count electron groups. I count 1, 2. This is 2, 3, and 4. So if I only have 2 groups, I'm in the linear section. Okay, now let's go a little bit higher. We've got trigonal bipyramidal. Bi meaning two. So we've got two triagonal pyramids that are attached to this centerpiece. Okay, this one does have two bond angles, a 90 and a 120. I want to be very clear. So we're going to pretend that if this were a spherical shape, which it's in spherical space, three-dimensional, it's got an axis just like Earth. So the ones going through the molecule up and down, that's the axial electrons or atoms. The ones going around the Earth or like the equator or around the molecule, so those are equatorial atoms. Okay, the equatorial atoms have this 120-degree bond angle, and the axial have a 90-degree bond angle. So really, that trigonal bipyramidal is like I put a linear together with a trigonal planar in different planes. The last electron group is octahedral. Now, I understand this one only has 6 bonded groups. However, remember, hedral means faces, so this has 8 faces. Okay, the bond angle for every single one of these is 90 degrees because in the XYZ plane, they're all perpendicular to one another. Now, I will never expect you to draw this three-dimensional one. This is what I will be looking for in drawings. Okay, so let's determine the molecular geometry of nitrate. First, you have to draw nitrate, which we have drawn before. So, basic 5 plus 6 times 3. Don't forget to count your valence, plus 1 because of that charge. And so this is 18, 24. I just used 6. Okay. I'm going to double bond this one because if I put 18 around the whole thing, then I've used them all, and nitrogen only has 6. Okay. Remember, on mastering chemistry for these, it's going to want you to put the formal charge on the atom itself. So this one is negative. This one is also negative. This one is 0. And nitrogen is plus 1. So yes, total, we do add up to -1. Also remember, it can be drawn like this with the charge on the outside. That's perfectly fine. Okay, just know on mastering chemistry, if a charge is shown, it's going to want you to put the formal charge on the atom itself. Okay, so now let's go ahead and do our molecular geometry. I've got 1, 2, 3 groups of electrons, and they're all bonded, so this is trigonal planar. While we're here, I do want y'all to get used to telling me the bond angle. So you just look on the chart, find the 3 bonds, trigonal planar, 120. Also, I'm going to start wanting you to write the hybridization down because those questions may appear. Now, hybridization is a pretty complex topic, but it's taking the different shapes of orbitals and making them into hybrid orbitals. Again, very complex. The orbitals themselves have very complex shapes, but then when I start hybridizing them, it's even more complex. Just know that the bond angles have set hybridizations, okay? And they're on the chart. Please, please, please use your chart. You have it. Use it. Okay, now let's do CCl4. So again, we have to draw it. That really should be an L. Okay, I've got 4 plus 7 times 4. Is 32. I just used 8, so I've got 24 left. Ooh, that's a bad 4. Okay. 6 on each. That makes 8 for everybody, which means everyone has their octet rule met. This one does not require any kind of brackets or formal charges. So this has 4 bonded groups, no lone pairs on carbon, so this is tetrahedral, which is 109.5 degrees. And then its hybridization is sp3. Again, just look at what the chart says. Once you've determined your bonds and your lone pairs, you just keep going across that row, and I would suggest just write it all. Okay? That way you don't miss any of it. Now, don't write it all on mastering chemistry, but make sure if I ask one of these pieces, you could pick it out. based on your drawing. Okay, so now we're going to talk about those lone pairs. First thing about lone pairs, remember they come in pairs. And again, we're still only paying attention to that central atom. Okay. Also, something you need to keep in mind is that lone pairs take up more space than a bond. Okay, and it's because their electrons are repelling each other in that lone pair, so they kind of push the other ones apart. So that does affect the bond angle. So I want you to write, if lone pairs bond angle is less than. So like on that last one we saw 109.5. If it had one set of lone pairs, it would be less than that 109.5. It's about less than 2.5 degrees. Now you don't have to know that. In fact, on most of the questions, they're just going to have the normal bond angle. They won't even say less than. But in reality, lone pairs take up more space. Okay, and in this image, you can see the bonding pair is pretty even. The lone pair, this is where that extra space is being taken up. So that's a lot more space. So the first one we're going to look at is bent. But this is for our tetrahedral original electron geometry. So I've got 3 bonded and 1 lone pair. Okay, so the electron geometry adds up to 4 total. So our electron geometry is tetrahedral. However, our molecular geometry, so if I do not pay attention to those lone pairs, then it just looks like I have a trigonal pyramid here. So this is called trigonal pyramidal. The bond angle is just slightly less than 109.5, and again, very slightly. We can also have 2 lone pairs, and really this is water, looks like this. Okay, so I've got 2 lone and 2 bent. So my electron geometry is still tetrahedral because I have 4 total. However, my molecular geometry is now bent because of these lone pairs. And I wrote 2 lone and 2 bent, but I meant bonded. There we go. Okay, so here, no lone pairs were at 109.5 degrees. 1 lone pair were at 107. 2 lone pairs were at 104.5. So remember, it changes by about 2.5 degrees. Again, you can just write less than. That's perfectly fine. So this one would be less than 109.5. And this one would be less than 109.5. Hybridization for all of these is sp3 for every single one of them. Okay, for trigonal bipyramidal, we've got lots of different options because we started with 5 and it goes all the way down to 2. So the first thing you need to know is that the equatorial are removed first. So the equatorial is where our lone pairs are going to be. Okay, I kind of like to explain this like weight. If you lose weight, you want to lose it around your body. So does this atom. It wants to lose it around, not up and down. Okay, so lone pairs come off the equatorial ones. This one is called seesaw because if you turn it on its side, it will look like a seesaw. Now, I know those aren't around as much as they used to be, but they're still around. Okay, this angle here is 90. And then here we've still got the 120. Next one you take off is still equatorial. This one looks like a T. If you flip it, it looks like this. So this one is called T-shaped. The next one you pull off, still equatorial. But here we're linear. I would say for linear geometry, we're at 180. Okay, for the bond angle. All lines have a bond angle of 180. Octahedral electron geometry is our last one. When we take one off, it doesn't matter which one you take off, but they arranged it to where it looks like a square pyramid. So 5 bonded and 1 lone is square pyramidal. Bond angle still 90 degrees. Square planar. So once I pull one off, I pull the opposite one off. So now we're in a plane. Again, this is so the electrons are in their farthest configurations from one another. Okay, so then we're back to 90 degrees. Square planar. I did miss this one. I guess I deleted that slide. It was this one. It's bent. So there are two bents. There's a bent 120 and a bent 109.5. It just depends on the total electron groups. So if you like this chart better, then print this chart. However, this chart does not have hybridization. So if you want that, this is SP, SP2, SP3, SP3D, SP3D2. Okay, the reason we have to jump into D orbitals are because, remember, P only had 3 lines. So once we get past that 3, we need to then start pulling from the D block. Also, remember, those expanded octets had to have D block electrons moved around so they could have that expanded octet. Okay, so let's talk about this. Suppose that a molecule has 6 electron groups, were confined in 2D, and therefore had a hexagonal planar electron geometry. If 2 of the 6 groups were lone pairs, where would they be located? Remember I said they needed to be opposite sides. So I would say 1 and 4 opposites. Okay, which statement is always true according to Vesper? So remember, Vesper pays attention to the central atom and then bonded and non-bonded. So the shape of the molecule is only by repulsions among bonding electrons. No. Shape of the molecule is determined by only non-bonding. No. Polarity, we haven't even talked about that yet for molecules. So D must be the answer, but let's check. We've got all electron groups on the central atom, which is important. So, okay, so here are the steps to Vesper. You must first have a drawn Lewis structure. You need to count your total electron groups, see if they're bonded or non-bonded or lone, and then you check your chart. So here we go, PCl3. So I've got P, Cl, Cl, Cl. I've got 5 plus 7 times 3. It's 26 bond. Subtract 6. Okay, so I've got 20 dots to allocate. I used 18. The extra 2 go there. So I've got 3 bonded and 1 lone. That is trigonal pyramidal. But here's the deal. It's also 109.5 or less than, and SP3. I would want all of those things on, like, I need you to know all of those pieces, because I could ask you only the bond angle, or I could ask you only the hybridization, and you need to make sure you understand that the shape is trigonal pyramidal based on your drawing. You have to draw them. If you don't draw them, you will more than likely get them wrong. Y'all have been doing this a while, and I watch kids do this all the time. Okay. Okay, they're going to go through all the steps. Great, great. Okay, let's do ClNO. How about ClNO? Got 7 plus 5 plus 6. That's 12, 18. Single. So that's 4. So I've got 14. 6 on each outside. That's 12. And then the extra 2 go in the middle. Now we notice something's wrong. What do? Oh man, not erase all of our stuff. We have to double bond, but only between the N and the O. And that is because only these 5 elements can double and triple bond to one another. So chlorine is not part of that. So chlorine cannot double or triple bond. Okay. So once we do that, I see 1, 2, 3 electron groups, but there are 2 bonded and 1 lone. So this is not trigonal planar. It's bent. And this is 120, but really less than an SP2. Okay, let's do another one. ICl4 minus. Okay, I've got 7 plus 7 times 4 plus 1 is 36. I'm going to bond. I've used 8. That is 28 dots. Sorry, that was kind of close. Okay, that was 24, y'all. So I've got 4 left. I is in row 4 or 5. Let me go grab my periodic table. Okay, I is in row 4. Sorry, 5. It's in row 5. So it can have up to 12. It currently has 8. So those extra 4, they go on the center. Okay, so now I've got all of mine. I do need to put brackets because there is a charge. So I've got 4 bonded to lone on the center, which is an octahedral electron geometry, but this is square planar, which is sp3d2 and 90 degrees. I do want to give you a little hint on the hybridization if you don't want to have to print it. Look, I've got 1 S, 3 P's, and 2 D's. That is equal to this total amount, 6. So they're always going to do that. They will always be equal to the exponent to the number of total electron groups. Okay, one more. I3 minus. So that's 7 times 3, 21 plus 1 is 22. Okay, so I'm going to do I, minus 4 is 18. 6 can go on the outside each. That's 12. And I've got 6 more. They have to go on the center. They must go in pairs. I need to give that brackets and a charge. So my center has 2 bonded and 3 lone. Okay, so this one is linear, which is 180, but it's sp3d because it's got 5 total groups. So you need to make sure you're careful with that, paying attention to, because there are 2 linears and there are 2 bents. You have to know which ones we're talking about. Okay, this page is just showing you how they'll be represented on paper or how they may be represented in the book. In the book, they really like to do like shadows and to show you, hey, some are going back and forth. A straight line, though, just means in the plane of the paper. This dashed one means it's going into the paper, so like towards the paper. And then the solid triangle means it's coming out of the paper if you were drawing them. Now, I'm never going to ask you to draw them in this little 3-dimensional way. Okay, so here we're showing linear, or the 2-dimensional, but also, well, really not 2-dimensional. We're showing you with the little dashed and solid triangles, and we're showing you the way the book draws them. So the way the book draws them is probably the way you're going to see them in Mastering Chemistry. Also, you can have bigger molecules, and you're going to start seeing that. Okay, you do need to make sure you're paying attention to the fact that, hey, I've got several central atoms. So I've got a central atom here and here and here and here. And you've got to be able to pull those pieces out. Okay, so each of them has their own geometry around them, their own bond angles, their own hybridizations. So you need to be able to cross out the rest of them. So what I would say, if you're looking at only nitrogen here, we're not even paying attention to anything over here. Nitrogen has 1, 2, 3 bonds, 1 lone pair. So it's trigonal pyramidal and everything that goes with it. Less than 109.5, sp3. Then you look at this carbon. I see 1, 2, 3, 4 bonds. That's tetrahedral, 109.5, sp3. This carbon, I see 1, 2, 3 bonds. Trigonal planar, 120, sp2. And then this oxygen, 2 bonds, 2 lone pairs. Bent, 109.5, really less than 109.5, and sp3. Okay, so you need to make sure you're comfortable with doing this on a bigger molecule, because in reality, most things are bigger molecules, not those little tiny ones we've been drawing. Now, I'm not going to ask you to draw one this big on a test, but I may give you one this big and you have to identify all the pieces. Okay, if you need practice, please, please, please reach out to me. I will be happy to help you. All right, so predict our geometry around each interior atom. So I've got CH3 and then OH. Okay, I've got 4, 5, 6, 7, 8 plus oxygen is 14. I've got 1, 2, 3, 4, 5 bonds, so that's 10. I've got 4 electrons left. They must go on oxygen because that's my only space left to put them at this point. So carbon is tetrahedral. It's got 4 bonds. 109.5 degrees, sp3. The only other central atom is oxygen. That one's bent. 109.5 degrees, less than. And this is still sp3 because it's based off the total. Let's do another one. Predict the geometry around each interior atom. So this is how, really, this is more of a skeletal structure than you'll see in OChem. But really, this thing looks like this. And it's got dots. Okay, so I've got 3 internal atoms right now, or interior. So this one is tetrahedral and everything that comes along with it. This one is trigonal planar. So 120, sp2. This one is bent, 109.5. And I do need you to specify which bent it is, because if you don't, I don't know if you're talking about 120 or 109.5. Okay, this is sp3, sp2, sp3. All right, that's it for today's lesson. The next video will include 5 and 6. Okay, y'all have a great day, and please let me know if you need more help.